Hi guys, I'm Ethan. I'm Eugene.
I'm Jing.
And I'm Jordan.
And I'm Yiing. Today we'll be talking about wireless power transfer, or in other terms, WPT.
In our modern world today, technology has seen many advancements and they have been significantly improved. One of those such technologies would be wireless power transfer, or WPT for short. It is the transmission of electrical energy without the use of wires as a physical link, and they are used to power electronic devices without the use of interconnecting wires, where they are inconvenient, hazardous, or simply not possible. WPT technologies make use of time-varying electric, magnetic, and electromagnetic fields in order to work. But as interesting as all this sounds, we may never truly understand how we can transmit power wirelessly until we learn the physics behind it.
So based on various studies, Faraday's law has been concluded to be the working principle behind wireless power transfer. And what is Faraday's law, you ask? Faraday's law is only applicable in closed circuits, and it states that when a magnetic flux linking a circuit changes, the EMF, or the electromotive force induced in the circuit, is actually directly proportional to the rate of change of the magnetic flux linkage. Electromotive force is defined as the electrical intensity or pressure developed by a source of electrical energy, such as a battery or a generator. In other terms, it is the energy per unit charge that is converted from other forms of energy into an electrical energy in order to move the charge across the entire circuit. So back to WPT. Basically, in practice, if I have two coils and a current is running through the first coil, the magnetic field from the first coil will be transmitted to the second coil, causing a voltage to be induced. For example, if I were to connect an AC power source to the primary coil, an alternating current will flow through the primary coil, causing an alternating magnetic flux to be produced. As the magnetic flux alternates, there will be times where it is perpendicular to the secondary coil. At this point of time, we say that it cuts the secondary coil, and electromagnetic induction occurs. This is when electromotive force is induced across an electrical conductor in a changing magnetic field. Thus, a voltage is induced in the secondary coil, which in turn produces a current as well. This current is commonly known as the secondary current. Thus, we can conclude that there is a power transfer between the coupled coils without the use of any physical links at all, such as wires, therefore proving that Faraday's law is indeed the concept used behind WPT. Based on Faraday's law, the rate of change of the magnetic flux actually determines the voltage induced in the circuit, and so when the voltage induced in the circuit increases, the current increases as well. Despite all this, WPT does not guarantee 100% efficiency. A percentage of the input power will be lost as heat energy through radiation at the primary coil and the secondary coil. However, this can be reduced by bringing the coils closer to one another, as a higher percentage of the input power will be received by the secondary coil this way. The further the coils are from one another, the higher the current needed in the primary coil in order to induce the same magnitude in the secondary coil as compared to when the coils were closer to one another, thus lowering the efficiency of the entire system. We'll be able to learn more about the efficiency of WPT when we compare different methods of transferring power wirelessly.
There are many different wireless power transfer methods, each depending on the situation and circumstances. Wireless power techniques mainly fall in two categories: non-radiative and radiative. In the near field of non-radiative, power is transferred through magnetic fields over a short distance using inductive coupling. Inductive coupling are mainly used nowadays, as it is mostly used for charging electric devices such as phones or even toothbrush, or maybe even charging electric vehicles. On the other hand, far field or radiative technique, power is transferred through beam of magnetic radiations, like microwaves. Although these techniques can transfer energy through a long distance, they must be aimed at a receiver like satellites. WPT has proven to be beneficial to our daily lives, but it has many risks. These electromagnetic radiations will be dangerous depending on the radius of its magnetic fields.
So one example that uses the idea of wireless power transfer actually came from one of the world's most famous physicists, Nikola Tesla, with his invention of the Tesla coil. There are many types of Tesla coils, those being the spark gap, double resonant, solid state, and vacuum tube. Though they share the same idea, the methods that they use to accomplish the idea is completely different from one another. For today, we'll be looking at the solid state Tesla coil, otherwise known as a SSTC. The solid-state Tesla coil replaces the conventional spark gap with a half or full bridge MOSFET, a type of transistor. A Tesla coil would consist of two parts, the primary coil and secondary coil, each of them having their own capacitors. The two coils and capacitors are connected indirectly through electromagnetic induction. Furthermore, a Tesla coil will need a high voltage power source in order to properly work. When the power source is hooked up to the primary coil through a transformer, charge begins to build up in the primary capacitor. Over time, this charge gets so large that the current flows out of the capacitor into the primary coil, creating an alternating magnetic field. The massive amount of energy causes the magnetic field to quickly collapse, generating an electric current in the secondary coil through electromagnetic induction. This energy sloshes back and forth between the two coils at several hundred times per second, charging the secondary capacitor in the process. Eventually, the charge in the secondary capacitor gets so high that the air resistance around the top load starts to break down and sparks could be seen coming out of it. We won't be looking at the sparks for now, but when there's a high frequency voltage coming out of the Tesla coil, it would be able to illuminate fluorescent light bulbs several feet away without the use of interconnecting wires. The principle behind the Tesla coil is to achieve a phenomenon called resonance. This is when the primary coil shoots current into the secondary coil at just the right moment to maximize the amount of energy transferred. The way the SSTC accomplishes this is to use an antenna to find and automatically tune the drivers to the coil's resonant frequency, the frequency at which the response amplitude is at a relative maximum. This, coupled with the interrupter and gate drive transformer, would allow the primary coil to shoot the current at just the right moment to maximize the efficiency and the amount of energy transferred into the secondary coil. As cool as the Tesla coil may have been, it quickly became impractical as it simply wasn't an efficient way to transfer power wirelessly. Clearly, shooting electricity everywhere into the air, whether it was being used or not, leads to extremely high wastages. Furthermore, the delicate electrical system housed in the Tesla coil would create a charged atmosphere, which certainly wouldn't be healthy for anyone living next to it. Even Nikola Tesla's most ambitious idea of transferring energy to the masses using his Wardenclyffe tower soon became abandoned 5 years after it began operating. Today, we may not be charging our devices through Tesla coils, but they do make for interesting light shows. Let's move on to the next example that uses the idea of WPT.
There are many devices that function based on wireless power transfer, which some of them being everyday items that we can see in our daily lives. Today, we're talking about wireless charging, a device known as inductive charging or cordless charging. Wireless charging uses an electromagnetic field to transfer power between objects through an electromagnetic induction. This is usually done with a charging station. Energy is sent through the inductive coupling to an electrical device, which can then use the energy to charge the battery or run the device. Induction chargers use an induction coil to create an alternating electromagnetic field from within a charging base. A second induction coil in the portable device takes power from the electromagnetic field through electromagnetic induction and converts it back into electric current to charge the battery. The two induction coils will combine to form a transformer when placed in close proximity. Greater distances between the sending and receiving coils can be achieved if the inductive charging system uses resonant inductive coupling. An example of wireless charging would be our modern smartphones. To charge our phones, we place them on an AC powered charging plate where it will connect magnetically. The charging plate houses a transmitter coil, whereas a receiving coil will be embedded in the phone. Alternating current in the transmitter coil generates a magnetic field which induces a voltage in the receiver coil, thus charging the phone. Other devices such as portable electronics, smart furniture, and electric vehicles all benefit from wireless charging, as removing the need of charging with wires will make it more convenient for the consumers. Aside from convenience, durability is also one of the main factors why wireless charging is highly recommended. Without the need of constantly plug and unplug the device, which will cause tear and wear on the socket and attaching cable, it will last longer and will not spoil so easily.
Moreover, it is also safer because no corrosion would occur as all electrical devices are enclosed, keeping them away from water and oxygen in the environment. There would also be lesser risk of electrical faults such as short circuits due to insulation failure, especially where connections are made and broken frequently. However, wireless charging has its own disadvantages in terms of performance. There are some wireless chargers which just simply cannot reach the same efficiency as traditional ones, meaning they will need longer time to fully charge despite being supplied the same amount of power.
Furthermore, although charging our devices through electromagnetic induction makes it a wireless power transfer, we will still have to attach the charging station to a platform, and the devices must be touching the charging plate at all times in order to be charged. This would be inconvenient as it is harder to operate your device without being able to move it around. Not to mention, inductive charging would also require drive electronics in both device and charger, increasing the complexity and cost of manufacturing.
So, here are two examples that uses the idea of WPT. All these new technologies seem great and all, but how do we modify them to be better in the future?
Technology has been improving and advancing day by day, and that applies to wireless power transfer as well. In fact, there have been a few modifications that has been done to WPT over the past few years. Recently, towards late 2013, researchers from the North Carolina State University have developed new technologies and new techniques to transmit power wirelessly from a stationary source to a mobile receiver, moving engineers towards their goal of creating highway power stations to recharge electric vehicles as they drive by. The researchers have developed a new series of segmented transmitter coils, each of which broadcasts a low level of electromagnetic fields. And with that, they created a receiver coil that can be placed in the car or any other mobile platforms as well. And the receiver coil has to be the same size with the transmitter coil. This is because coils of the same size can transfer energy way more efficiently. The researchers also modified the receiver coil so that when it comes into range with the transmitter coil, it is able to couple with it, allowing the specific transmitter coil to increase its current, boosting its magnetic field strength and related transfer energy by 400%. The transmitter's coil's current will return to normal levels once the receiver moves out of range from the transmitter. WPT is also used in wireless sensor networks, and wireless sensor networks are used nowadays to detect and measure the health condition of bridges. However, due to battery life, it critically restricts the application and maintenance costs of this system. To overcome it, WPT is used at ultra-high frequency band to supply current wirelessly to the system. This power transfer system is based on electric waves at 950 MHz and is also redesigned for tiny power submission to this system. But to achieve all that, we must first aim for a way more better and a way more efficient WPT system. Researchers from the ITMO University and the Kiun Research Institute has recently developed a way more efficient WPT system in 2016. One of the first changes that was made to this system was to replace traditional copper coils with spherical dielectric resonators. And another change was to use higher order resonant frequency mode, which is called the magnetic quadruple mode. The group discovered that operating the system at quadruple mode, not dipole mode, not only increases the efficiency of the system, but it also makes it less sensitive to the random orientation of the transmitter relative to the receiver. The possibility of random orientation is an important step to more practical commercial wireless charging stations, and at the present, wireless charging presumes that one has to perfectly align the device on the charging pad, but quadruple mode does not require such perfect alignment. I can't wait to see what all these new discoveries can bring us.
So here's everything you need to know about wireless power transfer.
We hope that you will learn something new from this video.
And to end it,
Thanks for watching! G causes the magnetic charge in the secondary capacitor. Just the right moment.
Energy, wire. Oh, current, not energy. Oh shit. And because of that, oh my god.
We're gonna be filming the sparks.